Hi, seems to be a perennial question about how to do linearly distributed loads. So these triangle things or these uh, trapezoidal type things here. So I'm going to go into that and I want to review a couple of important bits. What we want to do is, since you hopefully already know how to do these things, these are concentrated loads. We have a goal, and that goal is to simplify the distributed loads to make them look like concentrated loads. Now, you may have already done this before using these types of loads. These are uniformly distributed loads that look like this, where it's consistent all the way across from left to right. But, and so, what we did is that we found the middle and we found the total force, and we just assumed that that force was right in the middle. And that goal is achieved by now we have this what looks like look like a concentrated load in the middle of this distributed load. We know the distances, we can use it and apply it, just in the same way that we would address a force like that. So um, so that's our ultimate goal. So we can do the exact same thing with these linearly distributed loads. So one thing we have to remember is that it's only applicable for finding the reactions. Okay, if you're going to be continuing on to shear force diagrams and bending moment diagrams, the answer is no. Okay, we can't. We can use the reactions that we get. That's fine for the shear force and bending moment diagrams, but these distributed loads are going to act differently in shear force and bending moment diagrams than a concentrated load. So the assumptions end right there. It's only good for finding the reactions, in this case at A and Z. So we've got, what do we do? Well, we do basically the same thing. The only question is that it's a little bit harder to get at this, but it's pretty dang simple. Um, the thing is, in a triangle, we still find the middle. The thing is, the middle of the triangle is not down the center, halfway between the left and the right. It is, understandably, one third. What I say, one third from the base, or the height here in this case, or 2/3 of its distance from its point here. And maybe I didn't draw that as well as I could have. There we go. And yeah, that's a little better. 1/3 from the base. So 1/3 from the height, this height thing here, the very end, or 2/3 from the point. And so then what is total value here? Well, I've got M here and D2 here. I have M as the highest uh, amount of the distributed load, and it starts at 0. So the average is half of that. So it's this basically the formula for a triangle: 1/2 M times D, or distance, whatever. So in this case, if I make D1 equal to uh, 2 meters, D2 equal to 3 meters, I'm going to make it nice and easy for us here, and D3 equal to 4 meters, and L equal to 10 meters. Then this should be fairly easy to do. I'm not going to go through all of that rigmarole for you, but the other thing is that M is, we need a value for M. So if M is 500 newtons per meter, we find the total value of the total value of this load is 1/2 m times d, so it's 1/2 times 500 newtons per meter times 3 meters. So it's 1/2 times 500 is 250 times 3, and that is 750 newtons. Okay, so that's the total load that's coming down on the beam at this point. Now, the next question is, like for P, we needed to know the distance from Z and the distance from A. We need to know this distance right here. And that distance, like I said, it's 2/3 from the point or 1/3 from the end. In this case, it's 3 meters, so 2/3 of 3 meters is 2. So we got 2 meters here, 2 meters to this point. Makes that a little bit easier to see. Okay, 2 meters to that point, and then another 2 meters to point A. So the total here is 4 meters. So when we do our sum of the moments about point A, you know, one of the terms, the term for this, is going to be 750 newtons times 4 meters. In this case, it's going clockwise, so that means a negative. So it would be 3,000 Newton meters around point A. Now, of course, there's other terms here. There's P, there's Z, but hopefully you should know how to do that by now. Okay, so that's how to do a straight up linearly distributed load that starts at 0, ends at some other value. But maybe you have something that looks like this. Now what do? Well, we break this up into 2 different loads. One is a uniformly distributed load, a rectangle, and then the other is a linearly distributed load, a triangle. So this whole beam thing becomes something more like this. Okay, so I'm going to redraw all of these. Here's Q. ZY. AY. D1. D4. And now for the tough part. Okay, we got D2 here. All right, so now we put down 2 loads. One is a uniformly distributed load. And this one is the short side high. So this one is M high. On top of that is a linearly distributed load. Yeah, it looks something like that. Yeah, it's hard to draw all those little ones. Okay, and it is the difference high. So it starts at 0 here, and this height here is N minus M because it's this section here. It's all this in here, and so this height here is N minus M. So we take this uniformly distributed load here, and we do the usual, it's halfway over, so this kind of thing, and it is m times, in this case, d3, and the distance here is what? D3 over 2. So, and the same thing over here, that's D3 over 2 there. And so the distance to AY would be see if I got this. Distance to AY would be D1 plus D2 plus D3 over 2. D1 plus D2 plus D3 over 2. So that's just where that one would be. So that should not be new if you've done any of these distributed loads, these uniformly distributed loads. But then we've got to do the triangle. And the same thing applies as to what we had before. It would be 2/3 from the point we have another phantom force here, and it would be 2/3 D3 to that point, and its total load would be n minus m, would be 1/2 of that because it's a triangle, 1/2 n minus m times d3. Okay, so if you wanted to put some numbers to that, maybe we'll make it a little bit more challenging here. So this is going to be 10, this is going to be 4 inches, and this is going to be 22 inches. This is going to be 20 inches, and overall L is going to be, you can call it 60 inches. So our sum of the moments about point A is going to have several terms, and one of them is going to be the distributed load. Oh, forgot to put the forces in here. So M is going to be 10 pounds per inch. N is going to be 16 pounds per inch. All right, so none of these numbers are terribly nice. Okay, and so this is going to be M times D3. So that's going to be 220 pounds times, now this total distance is D1, D2 plus D3 over 2. So that's 10 plus 4 plus 11 times 25 pounds. And then the triangle part, the linear distributed load, 2/3 D3. So D3 is 22. So that's going to be 7 1/3 times this distance here is 16. Sorry, this difference here is 6. Okay, so it's not too bad. So I've got 22. Watch why I use the units, okay? So I'm going to calculate this out here. This phantom force here is going to be 1/2 n minus m. So what's that? 1/2 n minus m, which is 6 pounds per inch, times times 2/3. Oops, nope. Times d3 total. Okay, so that's 22 inches. There we go, 22 inches. All right, so 1/2 times that is not going to be too bad. So 1/2 times 22 is 11. So we got 66 pounds is the total of the triangle. Now we take that 66 pounds and we multiply it by, make sure you do this right. This is 10 plus 4 plus 2/3, right here. 10 plus 4 plus 2/3 of 22. So 10 inches plus 4 inches plus 2/3 times 22 inches. You might think I'm crazy, but I'm going to put this all into fractions here. So this is going to be 30/3 inches plus 12/3 inches plus 44/3 inches equals, okay, you got 42 plus 44, 86/3 inches times 66 pounds, 86/3 inches. But see, I can do this all without using a calculator or ridiculous decimal places because I can cancel out 66 and 66 becomes 22. So now I can do 22 times 86, and then maybe I should use a calculator, but I don't come up with some stupid 0.3333 or 9999 or whatever it is. So I'm going to do that. 22 times 86, 1892. Okay, so there'd be other terms in here as well. Okay, fine. So this would be 1892. Does have that right? 1892 inch pounds, and that's clockwise, so it's negative. And this is going to be 220 times 25. That's 5,500. So that's negative 5,500 inch pounds. Okay. The other terms I'm going to let you deal with because those are fairly easy to work with, and hopefully you've already done those. But that's just another example of how to deal with these linearly distributed loads. You break them into a rectangle on the bottom, triangle on the top. Make sure you've got the fractions right. That's 2/3 from one end and 1/3 from the other end, from the high end. And that's where that center, or actually we call it a centroid of the triangle is. And we assume that the entire load is there, just like a concentrated load is. And we can calculate how much load there is by just using the area of a triangle, but it's not the usual units of the area of the triangle, which brings me to my last point. Notice how this set of units is pounds per inch, and we end up instead with pounds times inches, okay? That's okay. I made sure that I kept those units straight all the way through. I've seen students all the time just start throwing in pounds per inch. That means you divided. That means the units are actually, one is divided by the other. And that is not the same as pounds times inches. That means they're actually multiplied. If you divided rather than multiplied, you didn't do it right. So make sure you use the proper units every step of the way. Okay. One more thing. This is the same thing as a dam. A dam is a linearly distributed load. Here's a dam, and if you'll notice that you've got water at the top and it goes all the way down to the bottom, and that is a linearly distributed load like this, because force equals mass times gravity times the height. So as you get further and further down, that height becomes greater and greater, and so it's linearly, the double the height, double the force. So we get more and more force as we go down. So uh, that is just one, probably the most common, but just one of many applications of a linearly distributed load. Okay, hope this helped, and good luck in your studies.